Alright guys, welcome back. I think I ended that video a bit early and I didn't really cover a concept that I wanted to do, so here it is right now. I really don't want to do a full lesson on 3.2 because I think it's heavily calculator based, and I'm not really comfortable using a I love my calculator very dearly. I love it in calculus, it's going to help you, but I really don't want to venture into calculator based calculations right now. So I'm just going to do a brief little lesson on chapter 3, section 2. And the thing that I'm about to teach you right now is going to be basically the only things that you're going to need to learn, or not the only things, but the most critical things that you need to learn for 3.2, right? And that is how the derivative of a might fail to exist, right? Now, a function will not have a derivative at a point where the slope of the secant lines fail to approach a limit as x approaches a, right? And there are 4 such scenarios. In the first scenario, so let me draw 4 xy axis first, and we can talk from here. Right, okay. So the first one, how would it not exist? Well, if you're, so if there's a corner on your graph, then there will not be a derivative at the point where things change, right? So for example, if you have f of x, right, equal the absolute value of x, it'll look something like this. I'm just drawing the parent functions right now, right? So at this point, right, the one-sided derivatives differ, right? So here you have a slope of possibly positive 1, right? And here you have a slope of possibly negative 1, right? And so here you really don't have, you really don't have like a slope right there, and it's not 0. Okay, just so you should know. So the first one is a corner, right? You can't have a derivative at a corner. Now the next one is a cusp, right? And you might be wondering what a cusp looks like. Well, put this in your calculator. F of x equals x raised to the 2/3. And what does this look like? Well, it looks something like this, right? It's like your sideways square root function, right? So at a cusp, right around here, right, you will not have a derivative because the secant line approaches infinity, positive infinity from one side and negative infinity from the other side, right? And this is basically an extreme case of a corner. So think of these two as one, basically, right? So far we have corner and cusp, right? What else? We also cannot have a derivative when we have a vertical tangent, right? And what does that mean? So that means if we have, for example, f of x equals the cube root of x, right? Or x raised to the 1/3, then you have something that looks like this, right? Yeah, like that. And so where the slopes of the secant line approach either positive infinity or negative infinity from both sides, in this case it's positive infinity, right? Then you cannot have a derivative at this point, okay? So far we have corner, cusp, and this is VT, vertical tangent. And the last one, a discontinuity. And we did this when we were talking about limits back in chapter 2, right? And you have a discontinuity. Okay? What does that mean? So once again, we go back and visit the greatest integer function graph, right? So here, a discontinuity occurs because for all values of x greater than 0, it's -1, while as for all values of x greater than or equal to 0, the value is 1. Thus, your slope up here or your derivative at this point will not exist, right? Simply because the left-hand derivative fails to exist, and it fails to equal the one from your right-handed, or it just fails to exist, right? They're both equal, but the left-hand derivative fails to exist.